Assalamu alaikum dear students. Welcome to the lecture of the classical mechanics. In this we will discuss the solution for the problem number 7.5, which says that consider a vertical plane in a constant gravitational field. We have a vertical plane which is in the constant gravitational field. Let the origin of a coordinate system be located at some point in this plane. A particle of mass m moves in the vertical plane under the influence of the gravity. So okay, particle is moving under the influence of gravity and under the influence of additional force which is equal to this, directed toward the origin. Choose appropriate generalized coordinates and find the Lagrangian equation of the motion. Is the angular momentum about the origin is conserved, and explain. We have uh, we have to find the appropriate generalized coordinate, then general Lagrange equation of motions, and then we have to find that the angular momentum is conserved or not. So let's go back to solutions. The first of all, we will be better if we choose the polar coordinate instead of the Cartesian. Since the mass is constant gravitational field, we can choose the gravitational potential energy of the mass to be zero along the horizontal dimension, because there is no change of height. So the kinetic energy of the particle is equal to m over 2 r dot square plus r square phi dot square, as we have calculated in the previous question. And potential energy is equal to u is equal to, because when we are given with the force, so we can find its potential energy u is equal to minus f dot dr, and this is the potential energy when the body will take some heights. So you know that this potential energy will be equal to mg h, and h will be equal to r sine of phi when body will be at some height. You know that when body will be some at height, so it's one of the component will be mg r sine of theta, mg r sine of theta, and the second another will be mgr cos of theta, mgr cos of theta, because vertical component is mgr sine of phi. So therefore our vertical is the height which will affect the potential energy, mgr sine of phi. Lagrangian will be equal to t minus phi, where we have t which is this m over 2 r dot square plus r square phi dot square minus potential energy. Okay, then when we put this into Lagrange equations, which is d over dt partial L over partial r dot minus partial L over partial r is equal to 0. When we put this Lagrange into this equation, it will give us equation for the radius mr double dot minus mr square phi dot square plus ar alpha minus 1 plus mg sin phi is equal to this. And when we put this Lagrangian into Lagrange equation for the theta, which is d over dt partial L over partial theta dot minus partial L over partial theta, when we put this Lagrangian into this equation, so it will give mr square phi dot plus mgr cos phi is equal to 0. And then we know that the angular momentum is defined as, since the angular momentum is defined as L is equal to mr square phi dot, and we know that say that therefore the angular momentum is not conserved. This is because the two forces acting on the mass subject it to some kind of torque which makes the system not conserved. And you know that d over dl over dt here is equal to these things. When d over dt, and we will put this equal to this angular momentum dl, and this term goes on the other side, it will become minus mg r cos of phi. In this case dl over dt is not equal to 0. It means our angular momentum is not conserved. And why this angular momentum is not conserved? Because if this dl over dt is non-equal 0, it means some external torque will be acting on this body, because of which our angular momentum is not conserved. Okay, so from this expression we can conclude that our total angular momentum is not conserved. I will stop at this point and we will discuss the next question in the next lectures.